Hello, good morning, good afternoon, good evening, wherever you are sitting. This is Guillaume Calfon, and I am here with the great honor to introduce a presentation by Mike Holloway. And I don't know, many of you already know who Mike is. Either you've read him or heard him or met him. If you haven't, I wish you that you will soon. So Mike is the president at Fifth Order Industry, and is one of our thought leaders in the matters that we are covering in this conference. And his title presentation is most simple, and it's one that is keeping me on the edge of my seat because I can't wait to see what the answer will be. And the title is How to Improve Any Lubricant Analysis Program. And I think all of us would like to know that. Before we go into the presentation itself, one last chance to play, last chance as far as I am as moderator. So this is the code for this presentation. Memorize it, write it down, take a chance to play. Hopefully you win, fingers crossed. And without further ado now, let's have a listen to Mike has to tell us about this.
Hi, my name is Michael Holloway. Today we're going to cover how to improve any lubricant analysis program. In the next 30 minutes, we're going to cover the utilization of data and how to manage it accordingly, proper sampling methods, setting alarm limits and targets, and tests that are most applicable for a given system. Our objective, getting the most out of oil analysis. The tools you want to do is to develop a process to set goals and key performance indicators by maybe partnering with your oil analysis provider, your lubricant supplier. You definitely want to use data as a tool. And then finally, implement oil analysis into your reliability-centered maintenance approach. Now, reliability, it's an attribute of any system that consistently produces the same results, preferably meeting or exceeding its specifications. Increased reliability decreases failures of machines, materials, but also methods. And this is going to require change. Now, change is no easy task. We take a look at some of the elements around change. Vision, skills, incentives, resources, and an action plan. That represents change, but remove one of those elements, change fails. For instance, remove the vision in your team, department, company. It's going to be confusion. Skills. You take out the skill set. That produces anxiety. Anxiety is really a function of being out of control. You have increased skills, you have more control over a situation, more confidence. You remove that, you become anxious. Incentives. Everyone's incentivized about something. Financial incentives, personal incentives, social incentives. Financial incentives, well, that could be a bonus or a raise, a commission check, whatever. Personal incentive, well, you've achieved something. Maybe you've got a degree or a certification or published something or be able to do 100 push-ups. Who knows? You have personal incentives according to a particular goal that's met. But you also have social incentives. One of the reasons why people like to put letters behind their names, to be socially recognized. Love to buy big homes and fast cars, expensive things, right? Wear the beautiful pocketbook that costs $2,000 or the watch that costs $18,000. That's incentivized. You take away an incentive, and it's going to produce resistance. That happens quite a bit. Resources. Every organization, every person, every department requires resources to get the job done, to achieve the goal, to understand the vision. You take out the resources, you become frustrated. You don't have the tools to do the job. And finally, the action plan. The action plan. The plan of action. You're going to lay it out. You're going to take into consideration what your overall vision is and the skills that are needed and the incentives put in place and the resources that you're going to require to get the job done. But it's a plan that's required in order to get from point A to point Z. And without a plan, there's going to be plenty of false starts. You're never going to achieve the change. Now, first and foremost, we have to define these goals that target different areas of asset reliability management. Some things we can focus on here, things like lubricant management, equipment management, and even maintenance management. Probably not a bad idea to write these things down. How are we going to go about equipment management? What's important to us? Obviously, uptime, reduction of downtime, having that particular asset with the most amount of availability. That gives it what's called its reliability entitlement. How are we going to manage that equipment? We're going to have to understand what the goals are. The second thing is our lubrication management. What do we want there? We want to consolidate. We want to extend drain intervals or maybe optimize. Things like that. Get a better storage facility. Maybe with oil analysis, we could actually get a better understanding how to utilize the data, make it more meaningful. And then finally, with maintenance management, what could that mean? That means trying to shift away from reactive maintenance towards a more progressive maintenance approach, where it's proactive. Well, oil analysis has its objectives. First and foremost is fluid management, be it the oil or asset serviceability, understanding contamination, and even establishing drain intervals. But it can also be used for predictive maintenance, understanding any kind of abnormal machine wear, help you plan out maintenance, and actually eliminate some repetitive problems. Oil analysis will help us with our reliability as well. We can take that oil sample and put it through a ferrographic analysis and actually predict failure, understand capabilities. This is going to help with root cause analysis and actually equipment lifetime projections. Now, what it looks at? Well, it looks at machine wear behavior and identifying problems at the initial stage of development can actually pinpoint component source wear, contaminants as well, from dirt, sand, and even products, water, coolant, fuel dilution in engines, and soot. Maybe the wrong oil was used, put on top of existing oil. Understanding various types of wear debris that starts to generate. The oil serviceability, the oil suitability for further service life, understanding whether it can be changed out or not, or if it requires any kind of offline purification or filtration, or if the oil in the reservoir needs to be sweetened or even changed. Now we're going to have to define our measurables. We want to correlate measurables to equipment reliability. Use oil analysis to do that. Examples are, like, say, for instance, wear metals and contaminants, maybe versus a work environment and equipment designs. This is all very possible. We want to establish root cause elements, optimum lubricant performance parameters, where we can actually start to have a good understanding and control of contamination and a better understanding of lubricant properties, how these things actually affect overall equipment reliability, but also perhaps understanding how lubricant properties can go forward and help us actually purchase better items in terms of greases and oils and so forth. Now we want to measure, obviously, understand how our program is actually performing. A successful program is dependent on tracking some key performance indicators, and these things are known as KPIs. KPIs can be broken down to two major classifications: logistical, time on oil, turnaround time for analysis, etc., or data mining, where we can actually start taking a look at property comparisons and wear and contamination, oil condition comparisons, component reliability comparisons, so forth. There's going to be a few steps to KPI development. The first of which is establishing goals and objectives. It's probably most difficult. Absolutely most difficult. A lot of times folks will take on big challenges. It's kind of foolish, actually. What you want to do is start out small, get a good win or two under your belt, and then build it from there. So if your department or your company, you don't have any goals or objectives set forward, you're not going to succeed. It's not going to happen. You have to set your goals, you have to set your objectives, and that is the most difficult part. Next thing we want to do is establish what are called the critical success factors, the CSF. We're going to derive those from our goals and objectives, and this is going to be measurable and a time frame. So you have a metric and a rate. The metric is something we can actually measure. The time frame, it's over a period, obviously, of days, weeks, months, quarters, maybe a year. The next thing is to establish the key performance indicators from those CSFs and putting those in place. Like I said, you can have several, actually. There's no reason why you can't, as long as they're making sense for the ultimate goal of being achieved. Now, the next thing, obviously, is to measure. Collect the data. And then calculate against the metrics and the measures, where we're looking at the percentages and the ratios and the averages and the rates that are being achieved. And then track that over time. I'll give you a minute to write that down. Now, taking an oil sample is very similar to taking a blood test. A sample is drawn, it's documented, it's delivered to a lab, it's analyzed, results are interpreted, a diagnostic report is issued, and then there's follow-up. I want to show the example. I've got a couple different KPIs here. The Asset Health Program of Processing KPIs. Here we got the process. Let's say Take an oil sample, send it to the lab, oil analysis returned. The KPI there would be the sample turnaround time. The process within is obviously pulling the sample, sending it to the lab, and then getting the oil analysis results returned back to you. Another KPI is maybe the number of notifications that are raised from that oil analysis. Is everything good in the green, cautionary yellow, or severe in the red? Something to take a look at, think about. Those are important. That's an important key performance indicator. Obviously, sample turnaround time is to get the data back is important, but also the number of notifications raised. We don't want to do oil analysis unless we're going to use the data, but notifications have to be raised. And then thirdly, is notifications converted to work orders for the planned work. That's important as well. And maybe if those work orders are actually completed and a completion timeliness, so the work is actually carried out. Now we're starting to understand how key performance indicators, right in this example right here, there's 4 of them, but we're using oil analysis just for that. Here's an example starting out. It's a little table. I want to jot this down. It's just some examples, for instance, the target and the actuals. It's just an example. The first of one is the transit time. A number of days between the sample date that you took it and you sent it into the lab. That's got to be small. It's got to be realistic, but it's got to be small. It can't be waiting around for 3 weeks, 4 weeks. Well, let's set a target of 3 days. And after, say, a month or 2, you start measuring stuff. I don't know, maybe even sooner than that. Comes out to be 5.25 days. Well, you're not hitting your KPI, but you got to understand what might be the reasons why. Second thing might be turnaround time. That's the number of days for the lab to measure the results and make them available to you. Now, laboratories, they'll provide you a turnaround report. And let's say you want to have it, say, in 2 days. Some folks want to have it same day. 2 days is reasonable. How about sample info accuracy? How well are your folks filling out those sample ID forms? That information is reported back to the lab through lube reports, so forth. That's the kind of thing that should have 100% target. Those forms should be filled out perfectly. Well, how about sample info hours? Can't tell you how important that is. That's information reported to the lab. Lets you know how much hours on that oil and a component, or maybe even when the oil was changed. Oil analysis labs can tell you that. We're going to have a target of 100% compliance with that. You can break it out as well. Look at oil hours, component hours, unit hours, oil change. Those are 4 different things we can actually measure. It's just an example maybe what the particular customer had done. They didn't hit it on all cylinders, but now let's say we do this for the year and then we decide we want to do another one. Add to it, maybe next year, next month, whatever. So a new one might be the alarm reduction. Reduce the amount of severities or cautionaries we expect. Percentage of alarms, be it abnormal or cautionary severe. Oil analysis labs can provide you that through what's called a sample alarm report. Right here, maybe you want to set your target down to 30. So you want to reduce those nasty alarms. Because you're here, you can actually start indicating where you're actually using oil analysis to reduce problems, reducing the alarms. Now, some sampling basics to consider. You always want to use a clean bottle, have good sample integrity. You also want to use a new piece of tubing every time you draw a new sample. You don't want to reuse containers, and that can affect the contaminant analysis later on. You don't want to reuse tubing either. That'll cross-contaminate your sample. Now, some general tips. Don't allow the sample bottle to become dirty or contaminated. You ensure that you can clean around the sampling area before taking any samples, and discharge a small amount of fluid into a waste container before taking an actual sample. And don't sample from a used filter or the bottom of a system pan. There's going to be materials down there that aren't indicative of the overall process. You want to use new sampling probes and tubing after each component being sampled. Make sure that you label all your samples accordingly. The divisions of analysis. The first is the execution of how the product actually behaves. And here we look at air release, resistance to oxidation, demulsibility, various tribological functions, including wear, failure analysis, and quality control, and in-service testing, contamination, condition of the equipment, changes in consistency, and the physical and chemical properties. What is the goal within the laboratory? Well, first and foremost, the quality and analytical laboratory should represent the value of allocation, encourage trust to the customer by providing useful results and expertise, be able to meet the specific needs of the customer. The fluid analysis, it upholds safety and health, upholds environmental safe practices, and applies a forensic science for the process of law and failure interpretation. What is the lab's role in sampling? Well, first off, initial responsibility does lie with the customer. We've got to make sure that the customer understands how to pull a proper sample so it doesn't have any bias, contamination, and is properly labeled. Supplied samples must have the lab's confidence in order to create a meaningful result. That's really important. The customers with limited knowledge of sampling will require expertise of the lab to move forward. And finally, the lab may recommend alternative sampling depending upon the results. That could mean if we see an uptick in a certain amount of wear metals in an ICP, perhaps ferrography is in order. ASTM has established 4 standards for sampling. The D4057, manual sampling for petroleum and petroleum products. The 4177 for automatic sampling of petroleum and petroleum products. 5854, mixing and handling of liquid samples of petroleum and petroleum products. And then the 7718, obtaining in-service samples of lubricating grease. What are the goals within the laboratory? Well, first and foremost, the task must be repeatable no matter who collects the sample. And secondly, the task must be narrowed for specific purposes such as wear debris, contaminants, even organic matter, and in the overall condition of the oil. The task must be accurate. This is so that it may reflect the current lubricant and machine condition, and over a period of time, you can develop a strategic wear pattern. Now, this graph example is taken from the 7720.11 from the ASTM protocol. An example of SPC where they actually establish several different limits, determine white, green, or red alarm limits. The first of which is a 1 sigma limit. 68.2% of the data sets, they fall within 1 standard deviation of the mean. That sample data, well, that's less than 1 or equal to 1 standard deviation from the center line. They're going to term that a white alarm limit. Now you have 2 sigma. This is going to be determined to be the warning limit. Now 94.45% of the samples may fall within the 2 standard deviations of the population mean. And here the sample data greater than 1 standard deviation away from the center line, with less than or equal to maybe 2 standard deviations away. And that's going to be termed a green alarm limit. And then we have 3 sigma limits. These are considered the control limits. 99.73% of these samples fall within the 3 standard deviations of the population mean. And abnormal to failure conditions are suggested by this particular data greater than the 2nd and less than or equal to the 3rd standard deviation away from that center line. We're going to give that one the red alarm limit. And then there's this 4th sigma, the variance. The 99.99% of those samples fall within that 4 standard deviation population mean. That's assigned, or that's a special case variance. It's often suggested that that data exceeds the 3 standard deviations from the population mean. Now, using the average and standard deviation for each of these data sets, I'm going to go about calculating the series of tentative alarms based on that test data. For a large number of assets, or fleets, you want to select data from at least 10 different consecutive samples for each machine in that equipment population. The more consecutive samples would be expected to improve the initial quality of the alarm limits being set. And a higher number should be considered when the alarm limits are applied to, say, critical equipment rather than non-critical equipment. You don't want to selectively pick through the data or randomly pick samples from the data for this data set. Selectively picked sample data, all those values can introduce some bias for sure. Randomly picked data from a measuring data set for a large fleet, that doesn't always reflect the failure modes either. Some tentative alarm limits can be set though with the data population, as small as maybe say 7 to 10. In these cases where all the identified failure modes and causes are not necessarily represented, lower quality alarm limits will still result. Now these alarm limits can manually be adjusted upward through experience according to similar machinery that you have. In cases where failure modes and causes are overrepresented, some higher alarm limits will result, and that's alarming. These alarm limits can be manually adjusted downward through experience with similar machinery, and in all cases, make sure that the alarm limits should be continually reviewed and updated either through statistics or experiences, accessing your CMMA programs, maintenance logbooks, interviews, great opportunity for failure mode effect analysis interviews. The more sample data, the more failure modes and causes are encountered, the better the data is going to be. Now here's an example of the cumulative distribution technique. An example here is a data set having some normal frequency distribution with a bell-shaped curve and two tails and so forth. Now viscosity measurements often fit this form. The sharing of viscosity and viscosity improvers, typically that's what happens when you shear down the viscosity, is the viscosity improvers are actually shearing down. Those polymers, typically polymethylmethacrylate polymers, they shear down, thins out the oil. You can also get from fuel dilution, contamination, that can occur as well with engine oils. That causes viscosity to decrease. We can also go oxidation and soot accumulation can increase viscosity. Now here's a useful way to actually establish a remaining performance value using some of this data here. We're looking to establish a tolerance alarm limit, in this case for viscosity. Now, the remaining performance value can be calculated according to the in-service values, the reference values, and the tolerance alarm limit that we've established earlier on. But keep in mind, in our equation here, our reference value has to be an absolute value. And here's an example of initial measured value are often low, often zero, and then increases as condition progresses. This particular scenario, well, we see this with acid number, oxidation, and even relative permittivity for examples of dielectric constant and so forth. The equipment applications where data follows what's considered a sawtooth trend, sharply dropping to a near zero after each oil change and then increasing over time. Now in this case, we can take the data and establish a remaining performance value where the tolerance alarm limit increases from the measured. This is done for particle count, oxidation, soot development, nitration, even fuel dilution. Qualifiers may exist. We got to apply if and then statements to 0% if it's greater than the tolerance alarm limit, and 100% if it's less than the tolerance alarm limit. Here's an example of a cumulative distribution curve for data having high reference skewed continuous frequency over a period of time. A great example of this is understanding base number, alkalinity reserve. These values start high and decrease over time, typically due to oxidation or the acid uptake, or we're actually measuring the depletion of the functionality of the sulfonates and the phenates. Determining when to change oil is well suited for this particular type of curve. Data is progressively changing, in this case decreasing, from oil change or even top-offs. So the data values do not consistently hover about a statistical mean value. Here we can take this data and establish a remaining performance value for something that decreases over time, much like we said, the base number. Here we're looking at the remaining performance value, and that's calculated from the in-service values, the reference values, and the tolerance alarm limit. Here's an example of a generic used oil warning limit table. This is just giving you an idea what something like this would go about looking like. And quite frankly, this is really generic. you should really establish your own warning limit tables according to your asset and your environment, your application. In this case, we look at various types of things like gears, hydraulics, all the way through to EHCs, and the various tests of viscosity. Now, typical warning limits for viscosity would be a plus or minus % off a new oil. That's a good place to start. For acid numbers, well, gear oil, if you have an increase of your acid number, 0.5 and up, that's alarming. Hydraulics, turbines and compressors, EHC is a lot more sensitive. As far as water is concerned, well, different assets can take on different kind of water. Gear oil, greater than maybe 1%, whereas hydraulics, less than 0.5%. Diesel engines, 0.2. Turbines and compressors are really sensitive to water. So you want to tighten up those alarms. And there's a whole host of other things we can take a look at as well. RPVOT all the way down to insolubles. These kind of tests, typically they're relegated for turbines, maybe compressors, but quite frankly, they can be very useful for other things. Using the RPVOT for hydraulic can be very useful. And some people actually do use it for gear and diesel as well. Density is actually a really good test to run. Typically, people never consider running density-specific gravity on used oil, but it actually does indicate contamination. Flashpoint, very effective, as well as insolubles. Here's another example of a used oil warning alarm table. Taking a look at other test parameters as well. Rust, air release and foam sequence, base number, even chlorine and glycol concentrations. And setting up alarm limits accordingly. Here's another example. This is fuel dilution. You won't run fuel dilution on gear or hydraulic, but you would run it on diesel. If you see an increase greater than 1 to 5%, it becomes alarming for sure. The SAE says you can have up to 7% fuel dilution in your engine oil. I tend to think it's got to be a lot less than that, but particle counts, hydraulic systems, very susceptible. Compressors as well. Gear oil, gearboxes, it can be a lot more robust. Wear metals and additive metals, obviously, 2 standard deviations away from the center line. In case of additives, well, regardless, those metals are always going to be in there. Really what we're trying to look at is functionality, but if we actually do see an increase or decrease according to some new oils or things that are added, often we can tell if it's been contaminated with a bad add. That's going to conclude our section on how to improve any lubricant analysis program. It's a short session, didn't last very long. A lot of material in there though. I hope you got something out of it. Feel free to drop me a line. Let me know what you think. Let me know if you need any help. You can always access me on the company website at fifthorderindustry.com or go to lubricant.training as well. That's a subsection, it's a division of Fifth Order. You can email me at Holloway at fifthorderindustry.com. Give me a call, text, WhatsApp, 214-450-7864. Thanks a lot. Looking forward to helping you out.
Thank you, everyone. It's been such a rich and complete presentation. We have no time for questions. Make sure to reach out to Mike if you have questions. And thank you for attending. And we'll see you on another occasion. Thank you. Goodbye.